Welcome back to this next video in which we are discussing quotient rings. Okay, so in this final part of this video then, what we're going to turn our attention onto is the first isomorphism theorem of rings, which gives us a good understanding of ring homomorphisms in terms of quotient rings. Okay, so if you've watched the video on ring homomorphisms and ideals, you might from that video still have a lot of unanswered questions about ring homomorphisms, and you might not have a full, complete picture of what they really are, whereas now what we're going to do is get a complete understanding of them. The first isomorphism theorem of rings is going to, just as the first isomorphism theorem of groups did, give us a complete picture of what ring homomorphisms are actually doing. Okay, so firstly, what I want to do is just remind you of what a ring homomorphism is, talk about what the image of a ring homomorphism is, which is something I didn't talk about in the video on ring homomorphisms and ideals, and remind you that the kernel of a ring homomorphism is an ideal, and then what we'll do is state the first isomorphism theorem and prove it. Okay, right, so we'll start off then with a reminder of what a ring homomorphism is. So a ring homomorphism then is a map that doesn't need to be bijective between two rings. So we'll call one ring R and we'll call the other ring R prime here. Okay, so I'll remind you that this doesn't need to be bijective. All it needs to be is a map from one ring, which we'll call the domain ring, capital R here, to another ring, which we'll call the codomain ring, capital R prime here. So to draw a little picture, here let's say this box is representing our domain ring, which we'll colour in orange here. Okay, and the homomorphism phi is going to take every single element in the domain ring here and map them onto elements in the codomain ring, which we'll have as this box over here. So we'll colour this one in pink here. So every element in the orange box here in the domain ring is going to be mapped onto an element in the codomain ring. However, it's not necessarily bijective, so it's neither necessarily injective or surjective. So it's not necessarily true that each element in the codomain ring only has one element in the domain ring being mapped onto it. It might be the case that multiple different elements in the domain ring are being mapped onto the same element in the codomain ring, and it also isn't necessarily surjective, which means that it isn't necessary for every element in the codomain ring here to have an element in the domain ring which was being mapped onto it. Okay, so it's just a mapping then, but it does have to obey three fancy criteria which make it interesting to study. So now let me point out these three fancy criteria. So criterion number one talks about how addition is compatible between the two rings. Okay, so it says that if you consider, well actually firstly let me just put in the first line, for all A and B that you can pick from the domain ring. Okay, so pick any two elements that you like from the domain ring, and I'm just calling these two elements arbitrarily A and B, so I'll just put them on my picture here. Here's A and here's B, so I've picked some arbitrary elements from my domain ring here. If you consider what is phi of A plus B, okay, where this is addition in the domain ring, so I'll colour it in orange because we're colouring everything to do with the domain ring in orange there. So you add A and B together in the domain ring, that's something you can certainly do. You'll get some answer which we're calling A plus B, and you're then asking, what does phi, this mapping here, map A plus B onto? Well, it needs to map it onto phi of A plus phi of B, where this is addition in the codomain ring here, so I'll colour that in purple. So A and B are both mapped onto elements in the codomain ring here, and I might just try and squeeze this in. So A will be mapped onto phi of A, and B will be mapped onto phi of B. Okay, and they're not necessarily distinct, they might be mapped onto the same thing. I'm just calling them this for want of better notation. Okay, so phi of A is what A is mapped onto and what phi of B, and phi of B is what B is mapped onto by the ring homomorphism. And here we can add these two answers together in the codomain ring, and that answer as to what phi of A plus phi of B is needs to be the same as phi of A plus B. So A plus B, I'll put this here, it must be mapped onto these two elements added together in the codomain ring. That's basically saying that addition has to be compatible between the two rings. Okay, so that's the additive criterion, and there's a very similar criterion for multiplication. So I'll keep this line here. For all A and B that you pick in the domain ring, it must be the case that if you consider what is phi of A times B, where again this multiplication here is in the domain ring, so we can add A and B together. We can also multiply A and B together, so multiply them together to get some element in the domain ring, and then ask what does phi map that element onto. It must be the same as what the mapping maps A onto, phi of A, multiplied by what the mapping maps B onto, phi of B here. Okay, where this multiplication now is multiplication in the codomain ring in pink here. Okay, so that's the multiplicative criterion, and then there's one criterion that people generally forget, but which is important, okay, and it says that the multiplicative identity must be mapped onto the multiplicative identity in the codomain ring. Okay, so this is the multiplicative identity in the domain ring, this is the multiplicative identity in the codomain ring. Okay, you don't need to state that the additive identity in the domain ring is mapped onto the additive identity in the codomain ring, because this one actually tells you that. Okay, criterion number 1 gives you that automatically, so this automatically, with the axioms that rings obey, implies that phi of the additive identity is equal to the additive identity in the codomain ring. So this is the additive identity in the codomain ring, this is the additive identity in the domain ring. And you might ask, well, why isn't it so for this? Why doesn't this automatically imply this? And if you want a more in-depth discussion of that, I discuss it in the video on ring homomorphisms and ideals, but it doesn't. Okay, and loosely it's because there aren't necessarily multiplicative inverses in rings. Okay, and that's why this doesn't lead to this being true in the way that this does lead to this being true, because of course there are additive inverses, whereas there aren't multiplicative inverses necessarily. Okay, right. So you do need to state that as a separate criteria that the ring homomorphism must obey. Okay, so if this mapping obeys these 3 criteria, then we call it a ring homomorphism, and it warrants study if it satisfies these 3 criteria. Okay, so that's a reminder of what a ring homomorphism is. Now, before I can state the first isomorphism theorem of rings, which is a theorem all about ring homomorphisms, I need to remind you of what the image and the kernel of a ring homomorphism is. And actually, we never actually discussed the image of a ring homomorphism in the video on ring homomorphisms and ideals before this video in the playlist on ring theory. However, you will most likely have seen the concept in group theory and potentially vector spaces, so it's going to be the exact same idea here. Okay, so let me just talk about the image of a ring homomorphism then. So we will once again denote it im phi, like so. So this means image of the homomorphism. Okay, and this is defined to be a subset, and we're going to see that it's a very special subset. It's actually a subring of the codomain ring, and I should have probably underlined it in purple therefore rather than orange. Okay, so I'll try and rectify that. So the image of the homomorphism is going to be a subset of the codomain ring here, R prime. Okay, and it's defined to be the subset that contains all elements in the codomain ring that have elements in the domain ring being mapped onto them. Okay, so I'll define it like so. It's all, let's call them little r prime, which is an element of capital R prime. So little r prime is just an element of capital R prime, such that little r prime is equal to some phi of R. Okay, where for some R is an element of the domain ring. So for some R is an element of the domain ring capital R. Okay, so to draw a picture then of this, and I'll just underline it firstly before I draw a picture of it. So we'll have it underlined in pink there. Okay, so to draw a picture of this then, let's take this picture and draw it bigger here. So here is our domain ring, capital R here. And once again, I'll colour my domain ring in an orange here, like so. And here is my codomain ring here, R prime. And once again, I'll colour this in pink. Okay, so the image of the ring homomorphism is just going to be all elements in the codomain ring which actually have elements in the domain ring being mapped onto them. So you remember me telling you that a ring homomorphism didn't need to be a surjective map. Okay, it didn't need to be bijective and one of the things, therefore, that it doesn't need to satisfy is surjectivity. So there could be elements in the codomain ring here, like this one here, that have nothing in the domain ring being mapped onto them. The image of the homomorphism is the subset of elements of the codomain ring that actually do have elements in the domain ring being mapped onto them. Okay, so if you're in the image of the homomorphism, if you're some little r prime in the image of the homomorphism here, I'll just underline the image of the homomorphism in green here, so here is little r prime, then it means that there is some little r as an element of capital R here, such that if we take phi of little r, it is mapped onto r prime here. Okay, that's what this criterion says. So elements like this one over here, which have absolutely no elements in the domain ring being mapped onto them, they are not in the image of the homomorphism. Okay, so the image of the homomorphism is just a subset of the codomain ring which have elements in the domain ring being mapped onto them. So it's just, you know, the normal definition of the image of a function, basically. Okay, right, now what we want to prove, the first thing we need to prove is that this is actually a subring, and the reason we need to do this is because the image of the homomorphism features heavily in the statement of the first isomorphism theorem. We can't understand the first isomorphism theorem unless we do this. Okay, so we do need to discuss the image of a homomorphism being a subring. Okay, so I want to check then that this is not just any old subset, it's actually a subring. Okay, so a subring is a subset of a ring which, if you put the restricted addition and multiplication laws on it from the larger ring here, it satisfies the axioms of ring theory in its own right. Okay, so we need to go through the axioms of ring theory and make sure that this subset with the restricted addition and multiplication laws on it from the larger ring obeys the axioms of ring theory. Okay, so let's start with the axioms that addition needs to obey, so it needs to be an abelian group. Now don't worry, this isn't going to take too long, because a lot of these axioms are just going to follow extremely naturally from the fact that they are true in the addition and multiplication laws from the larger ring. Okay, so let's go through the 5 axioms then of an abelian group for addition. Okay, so the first one is closure, and this becomes really important whenever we're talking about substructures. Okay, so we need to make sure that the image of the homomorphism is going to be closed under addition. If you take any two elements in the image of the homomorphism and add them together, so I should be writing this down, let's say for all, and how am I going to denote them? I will always denote them with a prime, so we'll have R1 prime, and I understand that that's confusing, and then R2 prime, so I hope this isn't too confusing. I put the prime there to show that they're in the codomain ring, and I'm now subscripting them to show that there's just two elements that I'm picking here. So these are from the image of the homomorphism. Okay, so I picked two elements from the image of the homomorphism, R1 prime and R2 prime. I need to show that it is the case that if I add them together, so R1 prime plus R2 prime here, that is also an element of the image of the homomorphism. Okay, so I don't add them together and end up outside of the image of the homomorphism is the big thing that I need to prove here. Otherwise this wouldn't be a subring, because its addition, its addition would be meaningless if we took away this portion here. Okay, because what you have to do when you imagine creating a subring is getting rid of all the other bit, imagining that it never existed. Okay, and if your restricted addition law on this subset has as an answer something out of here, then that becomes meaningless once you've destroyed this bit. Okay, so we have to make sure that that's not true. Okay, so R1 prime plus R2 prime, where of course this is addition in the codomain ring, but I won't bother colouring it in purple there, needs to be an element of the image of the homomorphism. Okay, so how am I going to prove this? Well, I need to show that this has something back in the domain ring here that is being mapped onto it, and I have to use the fact that these two have things in the domain ring that are being mapped onto them. Okay, so what I can do is, because R1 prime and R2 prime are elements of the image of the homomorphism, I can write them as phi of, let's say, R1, so I've got rid of the prime now. R1 is the element in the domain ring that was being mapped onto R1 prime in the codomain ring. Okay, so because it's in the image of the homomorphism, there must exist an R1. Okay, and of course, because we aren't assuming that the map is injective, it might be the case that there are more than one possible thing that would be mapped onto R1 prime here. I don't care about that, just pick one of them. All I'm saying is that there has to exist a thing that we can put in this position here. Okay, so it doesn't matter if there are degeneracies, just pick one of them. And the same is true for R2 prime. So R2 prime here, again, this can be written as phi of some R2, which is from the domain ring. So I'll just underline these in orange here. Okay, so now if we're considering what is R1 prime plus R2 prime, and even though I said I wasn't going to do this, I think I will colour that in pink here. If we're considering what those two things added together in the codomain ring is actually going to be equal to, we can just substitute in these things. So this is going to be exactly equal to phi of R1 plus phi of R2, okay, where this is addition in the codomain ring. But of course we can now use the compatibility of addition up here, okay, and rewrite this like so as phi of R1 plus R2, like so, okay, where that addition here is now addition in the domain ring, so it's in orange now. Okay, and that's exactly what we wanted to do, because look, I've now written R1 prime plus R2 prime as phi of R1 plus R2. R1 plus R2 is just some element of the domain ring, capital R. So I've now written it as phi of some element of the domain ring, which is exactly what it needed to be written as in order to qualify for being in the image of the homomorphism. So this is equal to this, ergo this is in the image of the homomorphism. Done. So it is now closed under addition. Now, axiom number 2 of group theory, associativity, we thankfully don't need to worry about associativity. It's usually a nightmare to have to prove that a composition law obeys associativity, but not in the case of substructures, because we assumed that the codomain ring was in fact a ring, so its addition had to obey associativity, and if the restricted addition law didn't obey associativity, then how would the larger addition law obey associativity? So because the initial ring's addition law obeyed associativity, we don't need to worry about the restricted addition law obeying associativity. So associativity we get for free, so we don't need to worry about that at all. Axiom number 3 is the additive identity. Okay, so we want to know that the additive identity in the larger ring, R prime here, is in the image of the homomorphism. Okay, so axiom number 3, we need to check that the additive identity is there. Now, why will that always be the case? Well, because we know that the additive identity in the domain ring is always mapped onto the additive identity in the codomain ring. Okay, that follows from the additive compatibility between the two rings, and also from the basic axioms that addition has to obey in the rings. Okay, and we do indeed show that in the video on ring homomorphisms and ideals. Okay, and it's also the same thing as happens in group theory with group homomorphisms. Okay, so the additive identity here will be mapped onto the additive identity here, ergo the additive identity here will have to be in the image of the homomorphism because there was an element in the in the domain ring which was mapped onto it. So that's fine. So that's nice and easy. And axiom number 4, which I don't know if I'll try and squeeze in here, I think I'll be crazy and try and do so. Okay, so axiom number 4, we need to check that it's closed under additive inverses. So we need to prove that if I have one element in here, so let's say I have some R prime, so for all R prime is an element of the codomain ring here, I need to prove that it's additive inverse. So I need to prove that there exists the additive inverse, which I'll call negative R prime, which is also an element of capital R prime, and that's it. We know the additive inverse will exist in the larger ring because it's a ring. We just need to prove that it's actually in the subset. Okay, well this is very easy. Now if R prime, no. Cross this out. We are trying to do this in the image of the homomorphism, not the larger ring. Get rid of this. Thought there was something wrong. Okay, so we want to prove that its additive inverse will be in the image of the homomorphism. So for all little r prime which is in the image of the homomorphism, we want to prove that its additive inverse in the larger ring is also in the image of the homomorphism. Now how can we do this? Well, if r prime is in the image of the homomorphism, then r prime will be writable as phi of some r. Okay, now I claim, and it's very easy to show, and indeed we will just show it, that the additive inverse of r prime, negative r prime here, is actually equal to phi of negative r. Okay, so I claim that additive inverses in the codomain ring, the things that the things that mapped onto them would have been additive inverses in the domain ring. So I claim that if R maps onto R prime by phi, then the additive inverse of R in the domain ring maps onto the additive inverse of R prime in the codomain ring. Okay, and how can I show this? Well, just consider adding this one to this one. Okay, if I want to prove that this is this thing's additive inverse in the codomain ring, then all I need to do is add the two of them together. So take phi of R and add it to phi of negative R here, and prove that that gives me the additive identity in my codomain ring. Okay, because that's the definition of an additive inverse, something that adds to the element to give the additive identity. Okay, so if I want to work this out, the way that I can do it is just by combining the addition using additive compatibility here, up here, and then I'll get that this is equal to, and I'll try and squeeze it in there, phi of R plus negative R, where this now is addition in the initial domain ring, so this now is addition in orange here, whereas of course this was addition in the codomain ring here, and of course R plus negative R by definition in the domain ring will give the additive identity in the domain ring, and then we know that the additive identity in the domain ring is mapped onto the additive identity in the codomain ring, so phi of the additive identity in the domain ring will give the additive identity in the codomain ring, hence this thing plus this thing will equal the additive identity, hence this thing is this thing's additive inverse. Okay, so the additive inverse of R prime then is going to be another element that's in the image of the homomorphism, because here it is. You can rewrite R prime as phi of some R if it's in the image of the homomorphism. Hence, I've now proven that phi of negative R will be its additive inverse, and ergo, it is going to be in the image of the homomorphism. So the image of the homomorphism is going to be closed under inverses. Inverses are going to be contained in there. Commutativity we don't need to worry about, because that will also come naturally from the fact that it obeys it on the larger addition. If you imagine the great big addition table on the initial ring here, on the codomain ring, on the entire codomain ring, obeys commutativity. It's symmetric down that diagonal line. But if you take a sub-portion of that, how on earth are you going to end up with it not being symmetric down the diagonal line? So commutativity will hold true, because it held true in the larger ring. Okay, so we have proven that it is a nice additive subgroup. Okay, we've proven that it's a nice additive subgroup. What we now need to prove is that it is in fact a subring, so we now need to go on to the multiplicative criteria. Okay, now, let me get another piece of paper. So, the multiplicative criteria then. So the first one we want to prove is once again closure, so I'll put this up here. So axiom number 1, we want to prove that if you take two elements of the image of the homomorphism again and multiply them together this time, you'll get another element in the image of the homomorphism. So let's have R1 prime and R2 prime back again, which are elements of the image of the homomorphism here. I want to show that R1 prime times R2 prime is also going to be an element of the image of the homomorphism. Okay, and this multiplication here is going to be multiplication in the codomain ring rather than in the domain ring. Okay, so this is the first thing that I need to prove. So this is very similar to addition then. I need to prove this is closed under multiplication. So, once again, what I'm going to have to use is the fact that these two are elements of the image of the homomorphism, and therefore they can be written as phi of some element in the domain ring. So R1 prime will equal phi of some R1 from the domain ring here. Again, I'll highlight the fact that this is in the domain ring by underlining it in orange there. And again, R2 prime will be writable as phi of some R2, where again R2 is from the domain ring here. Therefore, if I want to multiply the two of them together like this, I can substitute in these things here. So R1 prime times R2 prime is the same as phi of R1 times phi of R2, where this is multiplication in the codomain ring here. And of course now I can use the fact that multiplication is compatible in this way between the two rings, and I can combine this into phi of R1 times R2, where this now is multiplication in the domain ring. And of course, I've done exactly what I did in the case of addition here. I've now shown that this is phi of some element that's in the domain ring, because R1 times R2, those are just elements of the domain ring. Whenever you multiply two elements of the domain ring together, you'll get another element of the domain ring, and therefore you are just taking phi of some element of the domain ring, which is exactly the sort of thing that's going to be in the image of the homomorphism. Okay, so we have got multiplicative closure. Next axiom is multiplicative associativity. We don't need to worry about that for the same reason as we don't need to worry about additive associativity. Okay, if it's true on the larger ring, it will always be true on the restricted down ring. Okay, axiom number 3 is then the multiplicative identity, so we have to make sure that the multiplicative identity is in the image of the homomorphism, so 1 has to be an element of the image of the homomorphism. Now, why is that going to be the case? Well, we state as much in the criteria which a homomorphism has to obey. Phi of the multiplicative identity in the domain ring had to be in the multiplicative identity in the codomain ring, remember. So the multiplicative identity in the codomain ring, therefore, is most certainly going to be in the image of the homomorphism, because look, it's phi of 1 in the domain ring. So that's absolutely fine. Okay, so we do indeed have the multiplicative identity in the image of our homomorphism. And then axiom number 4 is the two distributivities. Again, think about it. If distributivity is true for whichever A, B, and C you can pick from the entire codomain ring, then when you restrict your attention down to a subset, of course it's still going to hold true for that subset. So again, distributivity, usually a complicated property, not in the case of substructures, because the entire thing had to obey it, and therefore this sub-portion is going to obey it. So we don't need to worry about distributivity. And finally, if we're working with a commutative ring, commutativity will follow very naturally as well. So if the codomain ring was a commutative ring, then indeed the image of the homomorphism is going to be a commutative subring. Okay, so indeed the image of a homomorphism is a subring of the codomain ring. Now, what does that truly then mean? Well, it means that if we have a ring homomorphism, so I'll write it out again. So here we have a ring homomorphism from our ring R to our ring R prime, then you can always reduce it into a surjective homomorphism. So if this is not surjective, what you can do is you can just imagine reducing the codomain, reducing it from being the entire of R prime to being just the image of the homomorphism. Imagine scrapping the excess bit. So if I get my picture back again, this bit is completely uninvolved in the actual homomorphism. It's not involved in it at all. Nothing from the domain ring gets mapped onto that. So you really don't need this bit to exist in order to understand this homomorphism. You can just think about it as a mapping from the domain ring R here onto this subring, which is a ring in its own right. If you do get rid of this portion, it's still a ring in its own right. Okay, so you can just think about it as a homomorphism from the domain ring here to the image of the homomorphism, and of course that will now be a surjective homomorphism. So you can reduce any non-surjective homomorphism into a surjective homomorphism by getting rid of the portion of the codomain ring that is outside of the image of the homomorphism. Okay, I think we'll have a break there, and then the next video what we'll do is talk about the kernel of a homomorphism, and then state and prove the first isomorphism theorem of rings.